So it's a pleasure to have today our member, Ruixiang Zhang, and he will talk about the stationary set method for estimating oscillatory integrals. Please.
All right, thank you so much for the introduction, and thanks for the invitation as well. So today I'll be talking about joint work, a joint paper with Sagata Basu and Chao Mingguo and Pavel Zorin-Kranich, and we name our paper the same title, so a stationary set method for estimating oscillatory integrals. I should say that mainly for polynomials of bounded degree. So here is my plan of the talk. As you can see, we will first review some backgrounds and relevant backgrounds about oscillatory integrals, and then describe what our method is, so the stationary set method that we call it. And then we'll describe one application, which is the convergence exponent problem in Terrace problem. And we use this method to get sharp results in dimension 2. And then I don't know how much time will be left, but my next plan will be to say a little bit about the proof of the application first. So that's the first part you see here, which requires, so we call our method a stationary set method, which is basically bounding integrals by the measure of sets. So the proof of the application will mainly contain understanding certain sets that we call stationary sets. And then that will be for the proof of the application. And I decided to say a bit about the main theorem in the last place, because this involves something that I don't usually see. So the proof of the main theorem, as you can see in the last part, will require a little bit of the so-called all minimal geometry, or all minimal, or theory of all minimal structures that I hopefully can explain a little bit about my understanding, because this is also my first time using this kind of things. So this will be the plan, and feel free to ask me anything during the talk. Okay, so well, let's start.
Could I just ask for starters, whether you need to have the polynomial is important, or is it just a convenience?
Yeah, well, I mean, it is important in this method. So as you'll see, hopefully very soon. Yeah.
Okay, thank you.
And it's also important to have bounded degree polynomials, so we don't look at arbitrary polynomials. Like we just focus on polynomials of degree less than 100 in dimension, say 5, and then that will be an appropriate situation to apply this method.
Mm-hmm. Good.
Yeah. Okay. So I'll be back on that later. But let's just start with some general backgrounds. And oscillatory integrals are usually integrals with purely imaginary phase, e to some purely imaginary thing times a cutoff function, as you can see here. And it naturally shows up in a lot of areas. So it's naturally an object in Fourier analysis, and also related to PDE and some analytic number theory problems and spectral theory and mathematical physics. So one general phenomenon is that if you look at this integral I and you ask how big it is, well, the absolute value there, it's usually much smaller than when you give up all the cancellations. So this is simply due to oscillation, because this e to the I times phi usually oscillates a lot. And for example, this is one question I will give to my math analysis students. Like if you do the integral of e to the, say, 10,000 times I times c from 0 to 1, then this is actually quite small. It's has the order of magnitude like 10 to the minus 4 just by simple integration by parts. So this is one simplest example. How to so some basic principles about this kind of integrals. So many of them described in Eli Stein's book. It will include, say, the first that you can do a partition of unity on psi to decompose this integral finer. And if you want to have a good upper bound on this integral, you can localize the problem by doing this around one interesting point. And what's an interesting point? Well, you want to have the gradient being 0. Otherwise, you just do the integration by parts that I just mentioned. So it turns out actually in dimension 1, we know the magnitude of this integral very well in a lot of situations, at least for analytic phases. the standard classical results involving when the corpus lemma, which says that if you have a derivative that's big, and depending on the order of the derivative, you would have a good upper bound of the integral, especially, especially if the other derivatives don't interfere. And there are asymptotic results that's, I think, related to this stationary phase, which we, which our name had originated in. But I should say that it's much more difficult in higher dimensions, and there are many open problems, and it becomes extremely complicated when this phi has degenerate critical points. And in higher dimensions, the critical points can look very complicated. And I'll just select one piece of research that has been done by a lot of people and just talk a little about it. So this kind of problem involves choosing a fixed polynomial p. So polynomials are probably the nicest, but also very general class of smooth functions of phases to look at, as long as I should have said this polynomial is real, so that it fits into the definition. Then you can study this oscillatory integral as shown here. You introduce one extra parameter lambda that's going to infinity. And then you look at the integral of e to the I lambda p times the cutoff function. You look at the behavior of this integral. You ask how big this is, and I think there's a problem in understanding this, and there's the Arnold hypothesis, saying that, well, I actually don't know what exactly is, but on the big picture part, it certainly says that the decay rate has to do with Newton polyhedron. So you can imagine when lambda goes to infinity, this decays, but might not decay like lambda to the -1, might decay slower or sometimes faster. But this hypothesis says the decay rate has to do with Newton polyhedron. And in a lot of important cases, this is confirmed by Warchenko as a very famous result. And then people like Greenblatt did some follow-up work more recently. And I think much less was known if you have more parameters than just this one lambda. So by having this one lambda, you're just looking at scalar multiples of a fixed polynomial. So what if we what if we just look at general polynomials, for example, then much less was known. And there are two results that I knew that I show you here. So there are stability results by Fong, Stein, and Sturm in, I think, probably dimensions 2 and 3. I'm not 100% sure, but stability results are like, if you have a decay estimate, then you can ask if you perturb your polynomial by a little bit, in whatever sense that is reasonable, do you still have this uniform decay properties? So this fits into the main theme of the story. And actually you allow multiple parameters because you're doing small perturbations. There's this when the corpus lemma in higher dimensions developed by Carberry, Chris, and Wright, which is actually quite nice, especially like if you're looking at the case when you have a polynomial in a given degree, in a given dimension at a given degree, then you would have a very nice one corpus lemma, as shown in their paper. But the one corpus lemma, they have nature that they're only useful if you have a good global upper bound of a given mixed derivative of the polynomial. For example, you assume on the support of this psi, the derivative of your polynomials, for example, in 2 dimensions, partial square x, partial square y, is always bigger than 1 on the support. And then if you also assume your polynomial has degree less than 100, then you would have the decay rate, I think, is to be lambda to the -1/4. But this is only useful if you have such a lower bound on the derivative. So these two are the results that I'm more familiar with, but I should say that much less was known when you look at multiple parameter settings. And Our work concerns the multiple parameter setting, and we have the following result. So this is the question that I was motivating. So let's assuming we have a polynomial, and in this talk we will assume it's on a cube of a given dimension, which can be anything. For example, you can look at the polynomial in 5 variables. And then we assume the cutoff to be the sharp cutoff of the unit cube. You will see a reason for that. This is one of the very few situations that I assume cutoff functions are not smooth. Well, but that will be the most convenient situation for us. And then I also assume our phase is a polynomial, so we don't have this lambda, but we require this polynomial to have a bounded degree. So for example, we can look at the integral over the 5-dimensional unit cube of e to the 2 pi p, where p is a polynomial of degree 100. So from the perspective of, for example, singularity resolutions, this is already getting extremely complicated. And our question is, what is the good upper bound of this absolute value of the oscillatory integral that you see here in the equation? So we have a motivation for this, and we will make this application clear to you in a few slides. But I think this is an interesting question in its own right. It wasn't clear to us already before we work on this project, how to bound.
You want to bound this sort of independent of the coefficients or uniformly or something like that?
Well, you want to bound this in terms of the polynomials, of course. In terms of the polynomial.
But what data? What data in terms of the polynomial?
The coefficients. So, for example, degree 100 polynomial would have 101 many coefficients. So, well, I mean, any kind of data. So we will let you know what kind of data we our bound relies on. So we made a new discovery with Basu Guo and Zorin Kranish. We found the general upper bound in this context. And the upper bound has a geometric interpretation that I'll show you in one slide, I guess. And we found this bound is also very good in a lot of cases that I'll also explain in a bit. So what is our theorem? What is our bound? It's right here. So now you fix the dimension, say 5, and the degree, say 100, and you have this theorem. So you can see that it's a simple inequality. On the left-hand side, you have this oscillatory integral. And on the right-hand side, you have something defined by geometry. Yes, actually, when we give it a name, we were inspired by the method of stationary phase. So we call this stationary sets. So for a polynomial p, we define L of p to be the supremum of a set where your value of the polynomial on this set stays in a window of length 1. So basically, intuitively, if you work with oscillatory integrals, you will see the phase oscillating back and forth. And then say if the phase move within 1 period, hopefully you wouldn't see much cancellations. And this is the intuition behind this set. So this LP is defined as the supremum over all the mu's of the measure of all the x's, such that mu is less than p of c less than mu plus 1. So this is our theorem that then the integral in absolute value will be bounded by the measure of this set with some constant depending on d and k, but we're happy with those constants. Okay. So any questions before I make more comments about this theorem?
So the constant depends on the dimension, but not on the degree of the polynomial.
No, it depends on both. So as you can see in the beginning, we fixed the dimension d and k. Well, it might depend on, well, theoretically it might be independent, but I believe it is dependent. But we'll be certainly happy if someone let us know it's independent of something. Yeah, but this is, in our result, it depends both on the dimension and the degree.
And is it explicit? Do you know how this constant behaves?
It should be able to make it explicit, but it might be something like double exponential, so quite bad. We didn't make any effort.
Okay, but maybe, I mean, you can show that it's bounded by it. at most double exponential, but maybe it's 1, right? Because, for instance, in
Well,
K.
I mean, theoretically, it could be 1, so we
Okay,
didn't
okay,
go
okay.
into that direction.
Okay.
I still believe it will increase with D and K, but I don't know. Yeah.
Okay, thank you.
Sure.
Is there any relation between this and the kind of Yomdin complexity that has been used in this context? You know that?
I'm not aware of this. I know
Because-
some work of Yomdin, but I'm not aware of.
Because it sort of bounds a number of components when you start to look at level sets, and it was used by Pila quite importantly in Pila-Wilkie. So I was just curious if.
Right. So as you can guess, this does have some connection with level sets, but we're, I mean, to spoil a little bit, we will be using integration by parts for monotonic functions. So basically, we will need some monotonicity theorem in the end that I'll say in the end.
Is it true that at the right-hand side you can write any number which makes the family of polynomials a normal family? Like, for instance, the sum of all the coefficients.
Well, I would guess this L of P depends a lot on the geometry of the polynomial or on the geometric properties of the polynomial. So, well, I mean, the problem is that, for example, if you're looking at a one-dimensional polynomial, that's simply, for example, lambda times x cubed, then this L of P will be like lambda to the minus 1/3, so around 0. So you would have this kind of power relationships if you really look into this L of P.
But since you don't specify the constant in the right-hand side, it does not matter.
Well, it actually does matter because the constant you don't allow it to depend on lambda, right? So my polynomial is lambda times x cubed, and you don't allow the constant to depend on lambda. You want it to be uniform in P.
There is no lambda in this inequality. So you want some inequality that is uniform with respect to some parameter. I don't see any parameter in this inequality.
Oh yeah. Such an estimate, I think, is certainly possible, but it's also possible that you lose more information if you insist on obtaining those estimates. Does this make sense? So for example, if you just want to use the sum of all the coefficients, right? Then a polynomial like lambda x cubed can behave quite differently from a polynomial like lambda x squared. So, but they have the same sum of the coefficients.
Yeah, but
Let's be sharp if.
Yeah.
So if P depends only on one of the variables, it looks pretty sharp, right?
Yeah, it is sharp in many ways. So I would discuss it in.
If P depends only on C1, for example.
Yeah, it's sharp in many situations, but it's not always sharp. So probably in a few slides we will see it. So I think at this point maybe I might as well move on to a few other comments that I prepared. I should have stayed on this slide maybe earlier. So yeah.
Go back a little bit, because it's like you have a family of polynomials and then you define a number for a family of polynomials, and there are many numbers that are comparable. And why this number that you wrote is better than any other if they are comparable within the family of polynomials of fixed degree in a d-dimensional space. So
what is number? Do you mean the implied constant?
Like you defined like
what you propose doesn't distinguish between lambda x squared and lambda x cubed.
Yeah.
So he wants to distinguish, but what you propose doesn't distinguish between that. No, I mean what Sasha was proposing. Something
so they would naturally have the different L of P, right? If you go back to the definition of L of P, they would have quite different L of P's.
No, I understand, but what Sasha was proposing, something in terms of the sum of the coefficients, wouldn't distinguish between lambda x squared and lambda x cubed, which is obviously what you want to do.
Yes.
So that's the reason why it's not in terms of a sum of coefficients.
Perhaps it'll be clear when he applies it and makes and actually uses what LP in some application.
Yeah. All right. Thank you for the question and the clarifications. Yeah, so some more historical comments. Hopefully you can see the last line. I couldn't quite see it, but I can see half of it. So as you can see, the implied constant here depends on the degree and the dimension, but not on the polynomial, which is extremely important. It's uniform on all the polynomials, no matter how their singularities might look like, for example. But one piece of information we want to convey is probably that because you have a bounded degree, so probably the most complicated singularity can be controlled, but we don't even touch this thing. So one thing I really like about our result is that we never touch singularities and its resolutions. As you can see, stationary sets are one kind of sublevel sets, and it's known that they have close relationship with the bounds of oscillatory integrals, and they are often stated as parallel problems in a lot of studies. For example, in the context where you have one parameter lambda, Warchenko and Greenblatt, as I mentioned, also studied the sublevel sets problem, which is a known problem that's well studied. And the relationship that's known to me is that, see the fourth item here, if you look at sublevel sets, then that's a sharp cutoff on the function value. And then you can expand that sharp cutoff into Fourier series. Well, you can first bound it by a smooth cutoff and then expand into Fourier expansion. And then you can bound the sublevel set by oscillatory integrals. So usually the estimate goes this way, that you have a good upper bound of oscillatory integral, and sometimes you can get good upper bound of certain sets, such as stationary sets, which is the case. And sometimes this is good. But the important thing is that our theorem goes in the opposite direction, and I wasn't aware of any such theorem before, that you can bound oscillatory integrals by the measure of sets, I mean, in this generality. We'll say that it's sharp in a large class of cases, and we'll make it hopefully explicit soon. And one more important thing is that the stationary sets, they are defined in geometry, and you don't see any cancellation in it, as you see in the oscillatory integrals. And the last comment, sorry, I don't know how to make this naturally into 2 slides, so I might have too much here. But the last comment is that the only proof we know is actually quite involved. It's not elementary. It uses a little bit of the theory of all minimal structures. So that's the comment. I believe I'm going into the application, so maybe it's also good to talk about one application to make more sense of this bound. Okay, so this is our main application. We were looking at the so-called Fourier restriction phenomenon for a certain manifold, which I also, by abuse of notation, call surfaces in this talk. And you fix the dimension and the degree. There's a very natural surface or D surface, if you want, in an Euclidean space that records all the monomials in D variables with degree less than k. So this is our map phi of dk. And we can define the Fourier extension operator, which maybe I'll go more into later, but now you just need to know the name and the definition for this surface as the following. If you have a function on the unit cube, d-dimensional unit cube f here, then E of f is a function on R of capital N. So in a space of much larger dimension, it's defined in the following way, that if you integrate over this cube of f against e to the 2 pi x dot product with phi of dk with this surface, and then with respect to this dc, and you get the Fourier extension operator. If you have f equals to 1, then this is an object that shows up a lot, for example, in the circle method. It's known as the singular integral there for many problems, especially for multi-dimensional terrace problems in our context. So there's this question about the convergence exponent problem in terrace problems, and it's raised by Hua when he studied terrace problems. So I wouldn't talk about terrace problems today, but since it's not directly related, but I'll just talk about this question. And then he only cared about, I think I have a typo. Do I have a typo? I think I have a typo. I'm sorry. I should say d equals to 1 instead of k equals to 1 here. So Hua's question was about the dimension 1 case. And then his question was answered by Arkhipov, Chupaikov, and Karsuba, and they raised the higher dimensional question. So sorry for this typo. And the question is that if your f is the characteristic function of the whole cube, then this integral, you just have e to the 2 pi x times phi of dk over the whole cube. And you want to determine the range of p such that this extension of 1 is in the LP space. So this is the question. And we got some nice result on this question by an application of our method. So we look at the d equals to 2 case, since d equals to 1 is already known. This is just some recalling of definitions. You're looking at the extension of this characteristic function 1, meaning that you plug in f equals to the characteristic function in the definition, and then we determine the sharp convergence exponent in this case, namely that if e of 1 is in LP, then this is equivalent to p strictly bigger than a certain exponent p2k. So I probably wouldn't go through the numerology too much, but I'll just mention this is a sharp result. And the case when d is equal to 1 is raised by Hua and resolved by Arkhipov, Chupaikov, and Karsuba, and also by Drury as a slightly stronger result. And the case when k equals to 2, that means for general d, for general dimensions, there's also a similar conjecture involving a general p of dk. But the case when the degree is equal to 2 is known by Monkenhaupt in his thesis. So this is these were the previously known results, and our result just resolves this problem for d equals to 2. And we will have a reason for that a bit later. Okay, so as an application, maybe let's think about what we want to do if we were to apply our main theorem to this problem. Then we can replace the oscillatory integral, which is e of 1, at any given point, because at any given point x, if you look at x dot product with this phi as in the definition, then that's a polynomial of degree less than k. So that's a polynomial in d dimensions with a bounded degree, and you can apply our main theorem to bound this e of 1 at any point by the measure of the stationary sets corresponding to that x dot product phi dk. So the problem is reduced to a problem involving the measure of stationary sets, and luckily this is a sharp reduction. What would be the stationary set here? Then you would have the following definition for each x. I should say x in R to the capital N. We can choose a mu such that this stationary set is maximal, and we define this set to be z of x. So this z of x is a subset of the unit square in 2 dimensions. This will show up very often later, and I have an example for you. For example, when k is equal to 2 and the dimension is also equal to 2, you have the total dimension for the surface to be 5, and then this surface is a 2-dimensional surface in R5. And assuming you're looking at e of 1 at the point 1, 1, 1, 1, 1, because the point has 5 coordinates, then what's the corresponding stationary sets? We're looking for a mu such that the set of C where mu is less than the sum of 5 monomials less than mu plus 1. So in this case, the polynomial we're looking at is the sum of the 5 monomials, because x is 1, 1, 1, 1, 1, and gives each monomial weight 1. And then we're looking for a mu such that this is maximum possible. And this will be our z of x for x equals to 1, 1, 1, 1, 1. And we also prove the sharp convergence exponent for the measure of stationary sets, as shown on the bottom. For p bigger than the same exponent, this function that I take the measure of z of x is in LP of Rn. I think this is a result I want us to digest well before I move on. So, any questions on these two results? Okay, so I plan to say a little bit about the general Fourier restriction.
The Terry problem, I don't remember the Terry problem, but Karatsuba was very interested in applying the sort of zero freeze region for zeta. Does it come up there in the constants?
We'll look into that. I honestly haven't looked into this problem.
Because you know, the mean value theorem, the Vinogradov mean value theorem, doesn't give you anything new on zeta precisely because of these kind of constants in the. You might look at it. Yeah, I'm just suggesting.
All right. Yeah, thanks for the comment. We haven't looked at that yet. Yeah. Okay, so one geometric interpretation of the stationary sets that I like a lot is that once you're fixing your x, then how to find the stationary set? Then you're actually looking for the largest possible intersection between your surface and the slab with a given direction and a given thickness. So you move the slabs around, you move the slab around in space and try to find the largest intersection. So for technical reasons, it's also with respect to the push forward measure of dc for natural reasons onto this surface. And my friend Zilin Jiang made this very nice picture for me. So this is a very nice geometric meaning of stationary sets in this Fourier restriction problem. Yeah, I should have mentioned the Fourier restriction problem, but before that, let me say one word about the sharpness. So this wasn't in our paper yet, but we discovered it shortly after we uploaded. So I guess we'll put it in the second version. A slightly more general context that for every algebraic variety, you can completely follow the above setup. You can take the intersection with the unit cube so that it becomes a compact thing. And then you can define a Fourier extension operator. You can define the stationary sets. And then you compare the two exponents that comes from the Fourier extension of 1 and the stationary sets. So we found that because of that other relationship that I mentioned, you can bound the stationary sets by the oscillatory integrals. And now we are bounding the oscillatory integrals by stationary sets. We found that it's in a lot of situations, this reduction is sharp, that P2 is actually equal to the maximum of P1 and the total dimension, capital N. This is completely general. This doesn't have to do with this particular surface. This means that if you want to study, for example, you take the surface measure and then you look at its Fourier transform, you want to ask which LP space it is in. Then you can also ask this question about the measure of stationary sets. And then this P2 is the maximum between P1 and N, which means if P1 is bigger than N, then P1 is actually equal to P2. So in this reduction, you don't lose anything. I think the P1, this is great for us because when P1 is greater than N, this is thought to be like the more difficult case because we have less decay rate. But in this case, we have very good control. And this is true. If you look at our exponent, that exponent is bigger than the total dimension in every for every degree in 2 dimensions. So this is just one comment that this reduction.
I'm a bit.
Yeah. In this situation. Yeah.
Isn't there like a full characterization if you're given like some complex algebraic and you want to calculate the best P? Isn't there like a way to say in terms of singularities what is the best P, or it's like an open problem?
Well, I mean, it certainly was an open problem for this surface that we were looking at. And I think it's known for every curve that's with each component.
Yeah. I'm getting confused as to, so your main theorem was sharp in dimension 2.
Yes.
And this aspect you're saying is completely general, this variety. I'm confused where we dimension 2 and when not.
Sorry, are you asking why do we need the dimension 2 in the main theorem?
No, this slide here.
Yeah.
is not dimension 2. Is that correct?
Right, that's right. So for higher dimensions, we have more technical difficulties so that we didn't pursue the higher dimensional case.
But this statement that you have on this slide is general.
Yeah, it's general. It doesn't have to do with dimension 2.
Okay.
Yeah. Yeah, this is also a curious discovery, but it's not very difficult. It's just by Holder and the above stated method.
If you compare with, excuse me, so if you compare with, because there were, so you say that your theorem is new in degree 2 as well, because there are already results that have to do with the Newton polynomial. Your theorem improves on that in degree 2, because in degree 2 it's very simple, the picture in terms of Newton polynomial.
Sorry, the degree 2 case, I think it's none, right, by Monkenhaupt. So
also it's no, but your theorem that you showed here related to Terry's that had to do with degree 2.
Well, so this problem in Terry's problem is known in degree 2 case before. So our theorem is in dimension 2 rather than degree 2. Meaning that we are looking at a 2 surface or usual surface, but we
and
allow.
It's still new in. It's new relative to what you could get by the Newton polynomial, because those are very precise. If you're in small dimension or small degree, you cannot do better than the Newton polynomial gives you.
Right. I'm not. So yeah, maybe I'll talk to you later about the ref. I'm not sure like which result you have in mind. So. Yeah, but I'll definitely talk to you later if that's okay.
Okay.
Okay. Yeah. Thanks. To our knowledge, like for example, this generality for arbitrary degree was certainly open, and I was only aware of the 2 results that I wrote here. So, yeah, I'll be happy to talk more afterwards. So since I probably don't have much time for Fourier restriction, but I'll just briefly mention it. So there's a general problem determining the Fourier extension. So I'll probably skip the motivation in 1 minute, but it's also meaningful to ask about the Fourier extension of a general function rather than just the function 1, and ask about which LP space it lies in. So as you can see, there are motivations about the properties of Fourier transforms, and Eli Stein started all this in 1970s. More technically, the Fourier extension estimates ask if you have E of F, LP is bounded by one version of it as is if it's bounded by the L infinity norm of F. But this is equivalent to what we were looking at when P is an even number, because you can do Plancherel, and then you're convolving F with itself many times on the special side. And when you're convolving 1 with itself, it becomes positive. So the result for 1 would imply the result for arbitrary F with an even exponent. So probably I wouldn't say too much about it, but a byproduct of a result is that if this critical exponent is even, then which means K is not congruent to 1 modulo 4, then we have the sharp Fourier extension estimates for this kind of surfaces for arbitrary degree K that's not congruent to 1 modulo 4. That's L infinity to LP, which I also feel quite interested about. So why do I decide to mention this at all? I just want to highlight one point that, so maybe one more comment is that when P of 2K is odd, we only get it plus the range P bigger than P of 2. I think I have another typo, I'm sorry. So when P of 2K is odd, not P of 2D, we only get the even number above it. And a little bit of history that there's a conjecture that this L infinity to LP Fourier extension estimate holds for P bigger than P of dk for general D and K, and the dimension 1 result is more classical. It's known by Drury, and his result is actually slightly stronger, not L infinity, but I think LP. But one interesting thing that I found about this is that, as some of you might know, there are many recent developments proving Fourier extension estimates. So I listed many of them. So bilinear methods, multilinear methods, and induction on scales, and decoupling and the broad narrow analysis by Bourgain and Guth, and polynomial partitioning. So we also tried some of this in this problem, in the Fourier extension problem, but we weren't able to get sharp range of P for any degree bigger than 2. So it seemed quite interesting to me that this new approach does better in our experience on this problem. But there's another very interesting perspective that some parts of our proof feel very much analogous to certain approaches listed above. Maybe I'll take a little bit to explain. Maybe next I'll just explain more about some ideas in the proof. So yeah, that's what I'll do next. Okay, so before I start the proof, maybe we have a few minutes for questions. Okay, maybe it's good to go into the proof sketch. And as I mentioned above, our strategy is quite simple with this Fourier extension of 1. By the way, I'm explaining the proof of this result just to be clear. The proof of this result. So we're determining the sharp LP space where this E of 1 lies in. And when we do this, we can use our main theorem to reduce this to an estimate about stationary sets. So I was listing the stationary set estimate that we needed in that slide that I'll go to right now. Okay, so this is a problem. We have this phi of decay, and for each x in R to the capital N, we can choose a value such that the stationary set is biggest. And we define this set to be z of x. I call this stationary set z of x. So just to be clear, x is a point in R to the capital N, but z of x is a point in the unit cube in 2 dimensions. So z of x is a unit cube on the surface. You can imagine it. And we have a simple goal. If you look at the measure function of z of x, meaning that for each x, you have a z of x, and you're looking at its measure. You want to prove this measure is in LP whenever P is bigger than the sharp conjectural exponent P of 2K. Okay, so the strategy is also quite simple, starting with dyadic decomposition. So we look at all the x where this measure of z of x is between delta and 2 delta for dyadic delta. Then we just need to bound the measure of this set. So L of delta, we call it. Another sanity check is that L of delta is in capital R to the capital N. So L of delta is in the large Euclidean space. And we want to bound the measure of L of delta. What is in L of delta? We have X in L of delta if and only if it has a large stationary set in R squared. So hopefully I've made this all clear, and I'll summarize this in the next slide. So we want to,
can you remember the notations that were used?
Yes.
Like there were some like P2K, phi dk, yeah, Zx, yeah.
This field. Okay, so let me think about how to explain this more. So we have a surface. We have a 2-dimensional surface in n dimensions. And for each point, we have a stationary set on this 2-dimensional surface. We use this set to bound the value of the Fourier extension on that point. The point is in n-dimensional space. So for each point in n-dimensional space, we have a geometric object in 2 dimensions. And now we're focusing on, so what do I put on the last 3 lines? Just means we focus on the set of points such that we have a relatively large stationary set. We have a stationary set of sides between delta and 2 delta. So whenever a point x has the stationary set size like delta, I put it into this L of delta. And I've thrown many points into this L of delta, which is a subspace of the large space. And now we ask, what's the measure of these points that such that each point has a stationary set with size like delta? Okay, hopefully it feels better. This is, so z of x is the stationary set. We want to prove the stationary set measure function is in LP. That's basically our goal. And a natural way, towards this goal is that we look at the set of points x such that the stationary set of x is between delta and 2 delta, and we put all the x together. And our goal is to give an upper bound of the whole set that we just put together. So how do we give an upper bound of this set that we call L of delta? We simply use the following strategy. We cover this set with rectangular boxes, and we just bound this measure of set by the sum of all the rectangular boxes. And it turns out to be enough. Yeah, it might get a little difficult to absorb this, but hopefully it makes some sense.
So this step of reduction to the main theorem, is not, you're not using the fact that you're in D equals 2, right?
We're not using the fact of D equals to 2 yet. So the difficulty haven't shown up.
Okay.
Right. Okay, so what's our strategy? We analyze each point x such that the stationary set is between delta and 2 delta, actually when the stationary set is bigger than delta. And we need to understand the stationary sets. So the first, as you can see in the first item, we first show that if the stationary set has measured at least delta, then it is morally a union of disjoint delta cubes. So you cannot get a fractal shape, for example. The reason behind here is that z of x, the stationary set, has finite complexity that I haven't talked about. And this is completely general that I probably wouldn't explain for now. And we now divide ourselves into two cases. And the first case is the concentrated case, where so we've shown that the stationary set is a union of delta cubes. And the concentrate case just means most of them is in a narrow strip. It's in a narrow vertical strip. Actually, we can put it that way. Once all of them is in a narrow strip, we have very nice symmetry of this surface, such that if you take a strip in the surface, we can do an anisotropy rescaling we can do an affine transformation of the, actually a linear transformation of the whole space, such that we send this strip to the whole surface. And then on the Fourier side, the space will shrink. And I will just say that using this rescaling idea, we can close the concentrated case by induction. I wouldn't say too much about it. It's an induction on delta, because if you rescale the strip larger, then the stationary set will get larger. So it feels like a problem with smaller delta. But we still have one more case, which we call the spread out case. The spread out case means that if we are not in this situation. And at this point, I'll just say that in the spread out case, we can fix a couple of delta strips such that no matter such that for most x with large stationary sets, you can find one delta cube on each strip that we just chose, such that the stationary sets has one of each of them. So I'll show you a picture on the next slide, hopefully to illustrate this. But I'll just make a comment that this feels to me very much like analogous to Bergen-Gou's broad narrow analysis. For those of you who are familiar with it, they developed this, I believe, at the Institute around 2009. So maybe it's good to look at this picture about the spread out case. So assuming our x is in the spread out case, then what we can do is that we can fix k plus 1. So k is the degree. You don't need to pay too much attention on it. But we can fix many delta strips, not many, I'm sorry, a reasonable number of vertical delta strips, such that if your x is in the spread out case, then you look at the stationary set. It's a subset in R2, and it morally consists of delta squares. Now, the conclusion is that for a lot of x, each strip that have fixed must contain one square that's shown in red, that's in our stationary set. But then we just realized that, for example, if these 3 red squares are all in the stationary set of 1 point, we can actually locate that point in the space. So if you look at the corresponding picture of these 3 squares on the curved surface, they will correspond to the so-called caps on the surface. And if all of them are in the same stationary set, then this forces our x to be in the convex body that's due to the convex Hall of the 3 caps. And we get information from there. So we show that most of the time the convex Hall is big enough so that the dual is small enough so that you've put your x, you've isolated your x into, restricted your x into a very small region. And then you will hopefully have a good upper bound on the whole set of such x. And then this is basically the story of the spread out case. Yeah, this can get a little technical, and I will happy to return it after my talk. But maybe for the last few minutes, let me completely go into a different area and try to say a few remarks about our main theorem that bounds the oscillatory integrals by stationary sets, by the size of them, and say a bit of words about the proof. So the proof actually reduces the oscillatory integral to a one-dimensional integral. And once you realize that, it will follow from a crucial geometric lemma about semi-algebraic sets, which I'll explain in a bit, and a simple integration by parts. So maybe let's get right to the lemma. So a semi-algebraic set is a finite union of subsets, and each subset is defined by a couple of equations and inequalities with polynomials. And we can call the complexity of set as the minimal possible sum of all the degrees of polynomials. So we only care about the concept of sets with bounded complexity. So you don't need to worry too much about this complexity notion. We just need the intuition that a set has bounded complexity if you can define it without too many unions and without too many polynomials, without too many degrees. Okay, so what is our lemma? Our lemma says, it's also a quite simple looking geometric lemma, that if you have a bounded semi-algebraic set K, then it makes sense to talk about slices of this set, especially we always assume K has a positive measure, otherwise this lemma wouldn't mean anything. Then we can look at the slice volume function, meaning that you can look at the intersection between our semi-algebraic set with a hyperplane that's parallel to the first n coordinate hyperplane. And then you move this plane around up and down, and you look at the slice volume function, you look at the volume of the slice and how it changes. And the important thing about this quantity is that it only changes monotonicity bounded many times, where this constant depends on the dimension and the complexity of the algebraic set. So this is the lemma. I'll show you a picture that illustrates it better on the next slide.
So this lemma, you really need semi-algebraicity, or it's enough O minimality or polynomially bounded O minimality, or well, probably it's pretty much greater generality, no?
Yeah, well, I mean, if you have polynomials, then you're always semi-algebraic, right? For general context in O minimality, because we didn't need it, we didn't think about it. But you're right that this might be more general than I described.
But then you must clarify something. Why are you using O minimality rather than just Seidenberg-Tarski?
Right. I will clarify it in.
Okay, all right.
Okay, but this is the theorem I want everyone to understand. So it's an elementary looking theorem that I have a semi-algebraic set, for example, the solid square that's slightly tilted, and I look at the volume of each slice, and I draw the graph on the left. I draw it vertically, so you can see that it increases and then stays and decreases. So the idea is that it wouldn't change monotonicity infinitely often. Actually, it changes monotonicity only bounded many times. So that's the idea. And finally, maybe I'll say a few comments about this lemma and this proof. Okay, so this is elementary, but we don't know any elementary proof. So it looks elementary, but it's not for us. In order to talk about the proof, we need the notion of semi-algebraic functions. Those are just functions whose graphs are semi-algebraic sets. And they would obey good rules, such as the property that I have that changes monotonicity only bounded many times in 1 dimensions, for example. But the crucial thing about our lemma is that you're seeing the slices, you're seeing the volumes. So you want to
explain that the integration does not preserve. Thank you.
Yeah, so integration will force you out of this class of semi-algebraic sets. So it doesn't preserve this class of functions. So we're forced to use something something heavier, which is known as the all-minimal structures. It's known, I think, by Cluckers and Miller in 2004, that if you integrate, then they still belong to a good family. I guess this that the family is good is proved elsewhere. It's also a deep theorem. And the family, I can only say its name at this point. It's known as the definable functions in some all-minimal structure. But once you have this family, you would have their members also have good uniform monotonic properties in 1-dimensional subspaces. The idea to prove the lemma is that you want to prove it for an arbitrary semi-algebraic set with bounded complexity. Then you actually look at a slightly larger space. You put all the semi-algebraic sets of bounded complexity together, and then treat each of them as a fiber. So you put all of them together and into a family. And this family also has bounded complexity. And you can integrate along some parameters and then use this property of all minimal structures to confirm this monotonicity lemma. And one last comment is that the effective, a lot of arguments in this area, in the theory of all minimal structures, can be made effective. But if you make it effective, I would guess this can be made effective, but it will probably be very bad dependence on D and K, so probably double exponential. That will be my guess. And I think I'll stop here. So thank you for your attention. Thanks.
Thank you. Questions?
Yeah, so I think you explained very clearly why you need to go beyond semi-algebraic. Who did you say proved that this class with integration is O-minimal?
Yeah, so this is in the all-minimal structure known as
you don't need Wilkie.
Well, someone else proved it.
Yeah, I'm asking who. Maybe Van den Dries?
I think Van den
Dries. Yeah, Van den Dries.
And his collaborators actually.
Yeah, he actually is a guy who is essentially invented this class. Yeah.
Right. He's the one who invented the all minimal.
Yeah, it's very natural from many points of view where you're trying to do something inductively like this, and your projections move out of your set for some reason. This is why Pila could only do dimension 2 surfaces, just like you. But let me understand something. What's 2-dimensional and what's not? You didn't. So the cap argument, was that the 2-dimensional thing?
Well, that's not 2-dimensional either. But I'll say that in higher dimensions. So yeah. By the way, I think Van den Dries and Marcinter and Marker, they proved.
Okay, Marker. Yeah, right. But Van den Dries is the inventor of this theory. Yep.
Right. That's one reference. Yeah. And so the reason that we weren't able to complete the higher dimensional analysis is that we can also execute this strategy. We can also try to ask for which x the stationary set has has like a magnitude like delta, we can also ask this question in higher dimensions. But we don't have a clean way to we don't have a beautiful like a clean way to construct a bunch of boxes such that their volumes are good enough so that it gives a sharp bound and each x is in one of those boxes. So philosophically, maybe one can, so maybe I'll just point out one philosophical obstruction to me in higher dimensions. So if you really look into our proof, which I won't be able to present to you, it involves some applications of Vandermonde determinants. So basically you take derivative in one variable and then you have Vandermonde in another variable and a bunch of linear things. So we reduce this problem into a linear problem. And for example, in 3 dimensions, I would imagine this not working anymore. And if someone really wants to get out of it, I would imagine one way to do it is to look at nonlinear real algebra geometric problems, which I was very fear of. So we certainly hope to look at this in the future, but it wasn't as simple as the way we found in 2 dimensions. So as you can see, the main theorem is completely general, and its sharpness is also completely general for sufficiently large degree. So these 2 are completely general. But in order to work on the stationary sets, well, stationary sets are simpler than oscillatory integrals in some sense, but they're also not that simple. You will have to understand for which polynomials they have a large stationary set, and this is a problem. Well, you just need to understand on average, but you don't. We don't always succeed. We only succeed in 2 dimensions.
Yeah, thanks. Just concerning Alex's question, in the case of, well, degree 2, but the 2-dimensional arbitrary degree, you could imagine somebody who knows singularity theory and understands all possible singularities that can form, also perhaps getting to the bottom of this problem, right?
That was basically my point, that if you have just a simple like degree 2 or something like simple.
But he's doing arbitrary degree in dimension 2, so that's quite complicated. That's all curves.
Yeah.
Yeah.
Real algebraic curves, they can be quite complicated. Yeah, it seems a natural way to go about this, especially inductively. Yeah.
So I do find it surprising this LP does as much as you've been able to prove it does. I would think you would need other, if you want to go high, if you want to get sharper results, you're going to need other geometric information, right?
Well, you do need geometric information about stationary sets, but that's slightly.
I mean, this LP is I mean, I know it can be quite complicated, but it's also, you can imagine much more complicated geometric information that you might have to use.
Right. We were a little surprised that this went through completely in dimension 2 as well.
Yeah.
And as I said, maybe in dimensions 3 and higher, if one were to understand stationary sets, he would have to go through more difficult real algebra geometric questions. I don't know.
Well, aren't there examples that that where it simply doesn't work, right? I mean, you have other techniques where the singularity structure better.
Right. So for the convergence exponent problem only, because of this theorem I'm showing on the screen, you will see that it has to work if the exponent is bigger than the total dimension.
Okay.
These 2 are basically equivalent. So this is going in a more difficult direction in a sense, so that it is sharp in certain situations, such as when P1 is at least capital N.
Okay.
Yeah. But understanding the geometry of stationary sets, this is also difficult in my opinion. Yeah.
Can I ask you, do you know of a theorem that is not improved by your theorem? So some case that you could do better by some other method than what you do? Do you know of a case?
So I'm asking too, yeah.
Yes. So one shortcut answer would be when, for example, in general, when the degree is 2 for arbitrary dimensions, this method is completely horrible because this P1 is much less than N. And just by this, you know it is not sharp.
Oh, I see. So it's really only, so it's only when very high.
Yeah, but another aspect of this theorem is that when P1 is greater than n, this has to succeed if the truth of oscillatory integral has this exponent P1, because you don't lose anything. For example, as I commented earlier, if you're fixing one dimension and make the degree grow, then there would eventually be a degree such that this has to succeed for all the degrees above that degree. Yeah, which I like very much, because the higher degree cases are thought to be more daunting, and I'm glad there's a way to unify all the higher degrees.
But you get a weaker and weaker, somehow weaker and weaker conclusion. Of course, it's expected, of course.
Yeah. So you lose track on the lower degree situations expected, for example, because of this theorem.
Yeah. Okay, thank you.
So the lemma you showed in the end, the proof, it looks quite similar to cell decomposition that you have in O minimal, right? So I wonder, so you don't really use the fact that you are, or do you? Can you generalize it not just to polynomials? Like if you put in the phases like reasonable functions definable.
I guess if we work really hard, we can. I guess the key is that if you integrate your class, you're still in an O minimal structure. I would imagine once it goes through, the same theorem would stand there, because it's a general phenomenon. Well, you also need to put everything into a family, and you also need that family to have to be definable in an O minimal structure. Once you have these two, I would imagine all the arguments will.
Yeah, but this is probably a bit more general. Okay, I don't remember, but I don't know if you add like irrational exponents or something. Probably this.
Oh yeah.
I don't know, but it looks very similar. So.
Okay. Right. Yeah. Thanks for the comment. We weren't realizing. Like,
I'm not sure, but okay. Thank you.
Yeah, that's definitely one thing that we can think about.
What kind of information about polynomials do you really use? Do you use that the first k derivatives are large in some sense, and then the rest of the derivatives are very, very small?
We don't really go in that direction. We just simply use their semi-algebraic. We just use the bounded degree polynomials are semi-algebraic functions of bounded complexity. That's really all we use. I should say that this is all we use in the main theorem. But after applications of the main theorem, for example, if you really want to work on the convergence rate problem, then you will have to do more analysis. You would have to, I would say, use the polynomial in other ways, but not like bounding a certain derivative or anything like that. So there are different ways. Yeah.
It really looks like that quantity that you wrote, like this L of P, it can be written like in terms of the coefficients of the polynomial.
Yeah. So this is possible in, I would imagine in many cases, but I don't know a unified way to, like, I don't know, for example, necessary and sufficient condition. But for example, in this convergence exponent problem, we really need something that's universally true to move on, I would guess. And I don't know much in that direction. It's certainly a direction to explore, but we didn't have an answer to.
No, it's just a statement about polynomials. The number that you defined, L of P, you can write a comparable number in terms of the coefficients at the very beginning.
How do you do that? You need to distinguish between lambda x squared and lambda x cubed. How do you do it?
In terms of the coefficients of the polynomial, it's clear. One coefficient is 0, another one is,
Right, it's perhaps possible, but also seems very complicated to me at this point.
I mean, the whole point is avoiding classifying all the possible singularities that can arise, and that's exactly what people don't understand, and that in general, you can, in principle, like just, if you take the problem of analytically continuing p to the minus s, the Gelfand problem that Bernstein solved.
Yeah.
If you have a resolution of singularities, that's how they solved it first. It's immediate, him and Sergei Gelfand. But the point is that you want to do it since resolution is very complicated, and especially when you're doing scaling arguments like this rather than a fixed p. So I think if p were just fixed and never moved, then, but he's got a family here. And
yeah, so it would be much different if p is a given multiple of a given polynomial. And there are studies that connects this to Newton polyhedrons that I knew of in many cases.
Sure.
This looks very, very natural for this aspect. Yeah.
Mm-hmm.
Very well. If there are no other questions for our speakers, so let's thank him again.
Maybe I'll stop sharing.
And have a nice evening, everybody.